Welcome back to Math 104. We found that if we flip a fair coin 8 times, the probability of exactly half heads, half tails, in other words 4 heads, 4 tails, equals 70 over 256. That's approximately 0.2734. To answer the same question about flipping a fair coin 10 times, that is, obtaining 5 heads and 5 tails, we need to do some expanding of Pascal's triangle, at least enough to get us down to this number right here. We need to compute 10 choose 5 to find out how many outcomes there are in the event that we're talking about. It's worth noting that in order to find this number, we didn't need to expand all of row 10 or even all of row 9. We could take row 8, which we had already found, and then find just enough of row 9, namely these two entries, in order to find ultimately the entry in row 10 that we're looking for. So we could have gotten away with much less work than is displayed here. Really just this information right here. Thus there are 252 distinct outcomes in the experiment of flipping 10 times, in which there are 5 heads and 5 tails. Out of 1,024 distinct possible outcomes total, that is only about 0.2461, which is less than what we got for 8 flips. Some students find this surprising. They find it surprising that it's harder to obtain exactly half heads, half tails on a greater number of flips. Didn't we say at the beginning of the course that the more times you flip the coin, the closer the relative frequency of heads tends to get to 0.5? Aren't we a little bit closer to the long run after 10 flips than after 8 flips? If you thought that, that was actually a very reasonable thing to think. The reason it doesn't quite work out is that the relative frequency of heads after many flips tends to get very close to 0.5, but it's not obligated to land exactly on 0.5 on the nose. Something important is going on here, and we can understand it better by representing each row of Pascal's triangle graphically. In particular, we could take, for example, row 4 of Pascal's triangle written out down here. For each number in that row, we can draw a rectangle whose height is that number. So above 1, we have a rectangle that's 1 unit high. Above 4, we have a rectangle that's 4 units high. Above 6, we have a rectangle that's 6 units high. Just as a reminder of what these numbers mean, the various words are listed here in L's and R's. If we think of the area of this shaded region as being 16 of these blocks, 6/16ths of the area corresponds to paths with an equal number of lefts and rights. So we have an interpretation of probability as area. This rectangle has height 6. It corresponds to a 6 out of 16 probability that there are 2 R's and 2 L's in whatever order. We can do this again with row 5 of Pascal's triangle, which corresponds to left-right paths with 5 steps. If we thought about flipping 5 fair coins, the picture would be exactly the same. Notice how much of the area lives in the middle. There isn't a single tall rectangle that lives in the middle. There are these two side by side, but notice how they take up 20 out of 32, 30 seconds of the total area. That's a lot of clustering in the middle. If we do it again, we find that only 20 out of 64 of the total area lives just in this tall middle rectangle, but if you include these rectangles right next to it, these correspond to paths that land in a location that's 1 away from the middle. That is now 50 out of 64, 50/64ths of the total area, which is quite a lot. As we keep doing this for lower and lower rows of Pascal's triangle, behold, the histograms keep getting more bell-shaped as the number of coin flips in the experiment, or the number of children in the family, or the number of random steps down that hexagonal grid increases. There's a wonderful online demonstration that helps us see what's going on here, and that helps us draw these as we go further and further down Pascal's triangle. Here we have a demonstration for random paths that are 10 steps long. This corresponds to row 10 of Pascal's triangle, because row 10 of Pascal's triangle knows about 10-stage processes like this. If we look at these rectangles drawn right here, that's exactly the sort of histogram that I was describing. And as we remarked about what each row of Pascal's triangle really means, we can think of this as describing an ideal dataset for the experiment of traveling along these random paths and taking 10 steps to the left or right along the way. If we had an ideal dataset of results, they would look exactly like this histogram. In practice, we may get something that doesn't look exactly like that, but in the long run, it should get closer and closer. So isn't that fantastically hypnotic? We can run this for a little while and see how the results accumulates. Sure enough, they are roughly in the proportions that we would expect, but not exactly. If we kept doing this long enough, the relative heights of these rectangles in red that reflect the actual results running the experiment, the relative heights would come to match the relative heights in this histogram. For 10 steps, we can already see how much clustering there is in the middle, but what's really illuminating is to see this for a much larger number of rows. For example, 40. First, let's look at this histogram, and let's notice that the event of getting an equal number of lefts and rights, and therefore landing back in the middle of the row, has a certain significant probability. Getting 21 lefts and only 19 rights also has a substantial probability. Getting 21 rights and 19 lefts has a substantial probability. So the results that are close to landing exactly in the middle also have substantial probabilities. So going back to our coin flip, and the question of whether flipping it many times is likely to result in exactly half heads, exactly half tails in the long run. It's unlikely to result in exactly half heads and half tails, because there are so many outcomes that are close to half heads, half tails, and those too have substantial probabilities. What's very unlikely is to be significantly far away from half and half. Notice how you can't even see the tops of the rectangles corresponding to getting all lefts and no rights, or even 30 lefts and 10 rights, or 30 rights and 10 lefts. If I could turn this dial up any higher and display 100 rows, this effect of clustering in the middle would be even more pronounced. Let's see how this actually looks when we run the experiment. Oh, isn't that beautiful to watch? Look at how clustered these are around the middle. Hardly any of these paths are making it outside of this fairly narrow middle channel. There is a much greater tendency for the lefts and rights to cancel each other out than our intuition might have suggested. Our intuition might have suggested that there will be more paths that are making it out here or out here, but there are hardly any. Feel free to go to this site and play around with it.